So let me welcome you all to the 2021-2022 version of Louisiana Aerospace Catalyst Experience for Students. It's a NASA program, so it has to have a nice acronym, LaACES. My name is Dana Brown. I'm a professor of physics here at LSU, and I assist in the program. I'll introduce to you the people who actually run the program shortly. So this is, let me summarize what we're going to do tonight. I'm going to introduce you to the staff of the program. I'm going to talk somewhat about what this whole program is about, what its goals are. You will learn a lot about setting goals and objectives in this program. I'll talk a bit about the course that we have developed, the student ballooning course. This course teaches you everything you need to know. There are really no prerequisites other than the willingness to commit the time and the energy. At various points in this project, you will have to produce documents. And we'll talk about what you need to do for that. I'll talk about some of the requirements for flight, what we actually do with the launch and chasing the balloon and recovery and some results. What you see in that picture on the right is what a launch typically looks like. This is, say, the balloons may be just lifted off, and all those little blocks down there are payloads, or there's a parachute. You see the weather balloon. There's a couple of radio beacons so that we can track, but that's what they kind of look like. So I'll introduce you to the LaACES management. So the fellow on the far left at the top, Greg Guzik, is the director of the Whole of Space program. So Doug Granger is, I don't know if Doug is on, but he is also part of the program. And Colleen, you have heard from. She's the assistant director of the Space program. The person on the bottom on the left is me a number of years ago. Now, the next one, Aaron Ryan, is actually the person who will be mostly directly working with all of you. He actually is the supervisor specifically of this LaACES program. And we have two people who provide technical support, Jill Junot and Josh Collins. They are both in our LSU electronics shop. They will be giving some of the talks, and they will be providing a lot of support for when you are building your payloads. So what is LaACES? So I already explained it's an acronym for Louisiana Aerospace Catalyst Experience for Students. It is basically a 2-semester long program where you take what we call the scientific ballooning course, and then you build a payload after you have learned what you need to learn. In order to, what your goal is to successfully develop a science experiment. You will then fly that experiment to 100,000 feet using a balloon, a weather balloon as the lift. In the process, you gain very practical skills in electronics, programming microcontrollers, project management, writing, and communication. Now, if you're in a STEM discipline, the sort of project management is something that you might find in an engineering program, but is not usually in the pure sciences, so that you should consider that a big plus. And I have heard that coming out of this program, the fact that you know how to manage a large engineering project, well, if you're applying for an entry-level engineering position, sometimes you will get bumped up to a slightly higher position because of it. Or you can say, I'm a physics major, or a biology major, and I actually know how to manage a project. Well, that's one of the fundamental skills of an engineer. So this program is targeted at sort of entry-level students in sort of STEM fields. That doesn't rule out somebody coming from another field. but that's sort of what the program was initially designed for. So you will learn as part of these in terms of building your project of goals and objectives. And you will have to decide what your goals and objectives are. That's a key portion of any large project like this. And so the goal is to inspire students to continue towards STEM-related careers. And under that, in order to do that, there are some objectives. So we're going to give you a real, authentic flight experience. It's not, this is rarely found in a classroom. Maybe an engineering senior design project comes close. You will learn how to become skilled in electronics, programming, microcontrollers, communications and public speaking. That in fact is one of Colleen's strengths. She actually has an English background and she will work with you on that. You'll learn to work in teams and use what you did to actually create a science payload for a balloon flight. And this is much more than just doing a science fair project. This is done with the same sort of steps that NASA itself uses. So if you look at the rovers that are now sitting on Mars, that's a beefed up version of the steps that you will go through. So you already know that. So you will communicate your progress by providing documents and presentations on a schedule. There are schedules to meet, and it's good to learn how you manage all of that. And then in the end, after you've built your payload and convinced us that it will work, we put it under a latex sounding balloon. It's carried to 100,000 feet, which is, at a sense, the very edge of space. The payloads come back and you recover your data. And so you've done a real science project. So I just want to, this is a bit of look back. So this program has been around for a long time. It was first started in the 2002 academic year and was just a few students from LSU. NASA approved the funding for the present program a couple of years later. And the first version of this ballooning course was developed. We have over 65 flights now since that time. A lot of them have been the LaACES. I've also seen things that were a biology experiment that looked at microbes living high up in the atmosphere. Those were payloads we have flown as well. And in the past few years, we did a major revision of the electronics. We're using a much more modern microcontroller, for instance. And we have managed to adapt a lot of this to COVID. And and so all this stuff is now online, which means you can see it if you more along your schedule. So the way this program is built is that now it involves students from basically any Louisiana institution. We also have done high schools. And the students are organized into teams of 3 to 4. That's a good size for a working group. You learn to accomplish things in teams, which is a skill in itself. This fall, you would be committing to bi-weekly 2-hour classes. They will usually meet Tuesday, Thursday from about 6 to 8. Each week, you have an hour or so of lecture and several hours of activities. This is not just listen and then go away. It's listen and then do something with what you just heard so that these skills get cemented. And everything you need to know, from electronics to programming, payload design, project management, how to design a balloon payload, the science behind it, all of that we will teach you. In the spring, you end up designing, developing, testing a balloon payload that is ready to fly. You have requirements in order to be put on the payload string. You have weight requirements, you have size requirements. If it doesn't meet those, it won't fly. So you learn to work toward a definite set of specifications. Shortly after the end of the spring semester, we all traveled to the Columbia Scientific Ballooning Facility, which is in Palestine, Texas, about 60 odd miles southeast of Austin, Dallas, where we will fly the balloon from there and then recover it in East Texas. Now, this particular program, you're being expected to devote 10 to 15 hours a week, every week. This may mean your spring break is spent working on your payload. And there are certain deadlines where you have to turn certain things in. We call those deliverables. Now, the way we're going to do this this year is we're going to conduct all the sessions for the ballooning program remotely. They will be, so if you want to see them, you'll do it the way you're doing it right now by a Zoom session. We're going to, each institution will have a document camera so that they can show what they're doing. If they're having trouble, they can put it under the document camera and we can peer at it and help them. These will all be recorded, but of course the real-time help will only be during the Tuesday, Thursday evening sessions. We're expecting that every institution will be responsible for all the material in the ballooning course. So the instructors at each institution are expected to kind of help with filling in some of the blanks. And the various requirements in these three-letter acronyms, which I'll talk about more, they are documents you have to create. Make heavy use of the material. So the material is all available online, plus you have all these recorded lectures. So for the fall, as I said, if you go to the LaACES website, you can get all the lectures, activities, auxiliary material, it's all there. It's a bunch of PowerPoint presentations. There's some 30 or so hands-on activities. All the lectures will be there. At the conclusion of this recording will be posted up there. I don't know when because I don't do that, but we have a YouTube channel where all the presentations will be. And there are two major projects in the process of the learning how to do this. It's a calibration report on a thing called the SkeeterSat, and I'm putting it all together at the end, capstone project. But each of the PowerPoints looks kind of like what you see on the right. So the hardware you will work with, first you learn, for instance, how to solder and then how to calibrate this instrument. It's called the SkeeterSat. It's an introductory circuit where it's mostly to learn how to do things. You learn how to identify electronics parts. You learn how to solder them in place. You learn how to test that it works. You learn how to calibrate the instrument. And you write a document describing the results of your calibration and what you've done. This payload, the data on the payload is handled by a microcontroller, an Arduino, that it will read the data. You will have sensors, you will have circuitry to read the sensors and present signals to the microcontroller, which will then record that data on a basically on an SD card. You will log all your data that you take as you ascend and descend on that SD card, and you will learn how to program that little computer there to do what you need to do. The other part of this is a logger. It's actually a circuit board called a shield that actually fits on top of the Arduino. It has a GPS receiver, which means that you now are going to know each time you take a piece of data where you are and how high you are. It has a place where you can add, say, additional sensors, and it is used for time stamping your data and logging your data. The little bright square on the left-hand side, I believe, is where the SD card goes, or maybe it's right above that. But you just put an SD card in there and it will get all your data. We don't usually try to transmit the data back down to a ground station. In the spring, you then use this combination of the Arduino Mega and the GPS logger to build what we call a megasat. This is the most common payload that we fly. You learn how to construct it. You have to work as a team during this whole thing. There, in fact, you will develop a team contract. Those of you who've done teamwork in classes before know that sometimes teams don't really work well together, but that's the way engineering projects are done. So you build a sort of framework that you can all work within and designate responsibilities and things like that. So you will learn a lot about how to manage a project. What's necessary? What sort of documents do you need? You need to produce, for instance, a document that says, this is our design, this is why we chose our design, and this is why we think our design is going to work. And we have certain things we have to have happen in order for us to fly a payload, and this is why our design meets those requirements. Part of this is you're building something, so you need to learn how to actually do mechanical design. So you will learn how to do mechanical drawings and you will build your payload. Everything is built here. The megasat pieces are bought, but and you have a budget, of course. But you have to build your housing and it has to meet certain standards. So you do all these various things and you will create documents that describe your design and why you chose that design. And these will be things that you have to do during the process. You can't just show up with saying, here's a box, let's hang it on a string. We need to know that you've actually made sure that it might actually work. So after you have put your payload together and done some testing, here at LSU, we have what is known as a thermal vacuum system, where you can put it through the sort of conditions that it would experience during flight. So you will be at various temperatures and you will be at very low pressure for a while. So you want to make sure that your payload works as expected. You know, you're going to be flying batteries to run everything, and they better work under these conditions. At the end of this, you will actually, there is a document called the Flight Readiness Review where you show us that from this document shows us that your payload is worth flying. And that's something you will do in the spring. All right. Now, a project like this is really quite daunting. It's nothing like what you've ever done in any of your classes, I would expect. You need to learn management and communications. Communication skill building is embedded. You will in fact learn the first part of this, which is how to keep a notebook record of what you do. And you will actually hear that presentation tonight by Colleen. You will create a document which describes the SkeeterSat, how it works, the assembly of it, the operation of it, how you calibrated it, and that document is something you will write individually and present. There is also since you are going to take sensors and interface them to the Arduino, you will learn how to build a document that describes how that information is going between the sensors and the Arduino. How you're going to get power to a sensor if it needs that, things like that. And you will produce documents and then a public presentation describing what you have done. There is also the management of a team. Your team will have a project manager of people tasked with particular things. You will probably learn that everyone needs to cross-train to handle everyone else's job. You will learn that actually people have spent a lot of time thinking about how to manage projects like this. And you will learn all of the language that goes into that. So you actually learn how a large, complicated project is managed. Of course, you only have, 4 people in it. You don't have 4,000 or 5,000 like a NASA project, like a mission to Mars might involve. So all projects that you're going to be doing have actually, this is what project management, the people who have figured out how projects actually work, have a set of phases. There's first a design part. So you design what you want. You decide what do I need? What do I want to do? I want to measure pressure, temperature, humidity from ground level up to 100,000 feet. I design something for that. At the end of that design, you produce a document describing your design and why your design is the way it is. Then you go in, and that PDR is a preliminary design review. You then go through the process of building something or filling out in the details, and you get to what is called the critical design review. At this point, you have something that it ought to be complete enough that you could hand it to somebody and they could just build it. You've given enough specifications that it doesn't have to be your job. And if you think about NASA, this kind of stuff, that every time they hand something off to a contractor and say, I want something built, they have to give them something sufficiently detailed so they can build what NASA wants. Then you end up building it. I mean, you've made a complete recipe on how to build what you want to, so then you build it. Then you have to make sure that what you built will work with the other things. This is called integration. So did I build it the right way so that I could put it in the payload? Is it too heavy? You will then do testing to make sure that it works. And at the end of that testing phase, where you have simulated it to make sure that it works, you will have what is called as the flight readiness review. And that means you will describe in great detail how you tested it and why you believe it is worth flying. Now, this sounds like a lot of work. What you will find is that you're taking your preliminary design review document, and it already has many of the things you need for the critical design. So you actually, in many cases, it's more like you have a document that you keep adding to. And the flight readiness review has all of the ingredients, all of the stuff you wrote for the preliminary design review and the critical design review are actually part of the flight readiness review. It shows that the testing you did does indeed make it fly, but you also need a description of what it was that you're testing. So you're building on these things, and there's a lot of reusing. And then you fly it. So there are requirements in this program. In order to be allowed to fly, so you have to have delivered the preliminary design review, the critical design review, and the flight readiness review at the date that it is due, and it has to be approved by LaACES management, so the folks you saw on the first page. The payload must successfully complete a thermal vacuum system test here at LSU. The actual presentation of the flight readiness, where you will summarize the flight readiness review document, is usually conducted at the Columbia Scientific Ballooning Facility. And you do your presentation, we sit there, and we decide whether you are ready to fly or not. So these are specific requirements if you're going to fly. So you're putting something up in the air, and the FAA is very concerned about people putting things up in the air because it creates a very serious risk for other people up in the air, like commercial aviation. So they have very specific weight and size requirements for anything that is flown. And in fact, interfacing with the FAA while we fly is in fact something that has to be done during the flight. They need to know when we launch, when we're back down, all sorts of things. So it's limited to a 500-gram weight, your particular payload. The FAA limits the total weight hanging on the string, and your payload can only be 500 grams. What you usually have is a box or a polygonal prism with sides that are about 15 to 20 centimeters long. I mean, you can make them longer than that, but that's more weight. The structure is usually constructed from polystyrene foam because that gives pretty good insulation. You have to make sure that your payload will allow a pair of strings to pass through it, because that's how it's going to be suspended. That's the two strings separated by 17 centimeters that pass all the way through the payload, and they're actually little binder clips, spring clips that are that actually hold the balloon on the payload string. You have to conduct some kind of science or technology experiment. You can't just put like a bunch of cockroaches in it and see if they survive the flight. It has to be designed, built, and shown to be fully space-worthy. That's a mistake there, May 2022. You have to complete the 3 major design reviews and the system test. And when you're done, so we usually fly early in the morning, we recover sometime that afternoon. You have a couple of days to get your data, and then you will do a presentation on what you learned. If your payload does not work, you will do a presentation on what went wrong. And you will do that presentation in front of the staff of CSBF and the rest of us.
Watching.
Good point. The question was, in a launch, how far does the payload actually travel from launch to recovery? And the answer was tens of miles. The core of the payload will be this thing we call the megasat. It has 2 temperature sensors, a humidity sensor, a pressure sensor, an accelerometer to measure 3 axes. You have one of these in your phone. A 3-axis gyroscope, so you can roughly orient yourself, and a real-time clock with a backup battery. The controller will be an Arduino Mega, and you will have this extra circuit board called a shield that plugs into the Arduino Mega for GPS data, and it will record the GPS data, which is in an NMEA format, onto an SD card. And there are various pieces on these boards where you, if you want to do other sensors than what is supplied, you can actually install those and the circuitry necessary to get good readings off of it. So that you construct this in parallel with all the other things you're doing, the various documents, and as part of the planning, you need to know what components you're going to have, how long it's going to take, how to interface additional sensors if you choose to do that, and so on and so forth. The thermal vacuum test, you'll come here. It's a big vacuum chamber, and we also have like coolers with dry ice in them to simulate the extremes of balloon flight. Everyone has to come to do this test. It's usually done in late April. The payloads are supposed to be completely ready, configured for flight, and then they're just cycled through the thermal vac system to see how they respond. And you get a bunch of test data back. Hopefully it says that it works. If it doesn't, then you have some stuff to work on. So this is the milestone schedule. Let's see, I caught all the dates, but the title needs to be fixed. I'll fix that. So your first Skeeter Sat report, your report on the first circuit you build. So there is a deadline for each institution, which means that that should be delivered to the lead faculty member there by that time, who should then look at this document and give feedback and fix it. And then it is transmitted a few days later to LaACES after it has been gone through a revision. You will discover that documents like this are not written in one sitting. There is a process of making a draft and reviewing and editing and making a draft and reviewing and editing. That is the way documents are prepared in the real world. And that's what you will learn through this. So there's a Skeeter Sat report and a capstone report. And that's kind of at the end, that's just after Thanksgiving. So that's at the end of the semester for the institution. And then at LaACES, it is due shortly before Christmas. You'll then have a team contract. Actually, the pre-PDR and the pre-CDR, we will not do this year. So I will take that out on the slides that go up. So you don't need to worry about those.
So it's not that we don't do it. It's that it doesn't come, the institutions don't submit those to the management people here at LSU.
Right. So you'll notice that there is a date, and we recommend that you do these as kind of a dry run before you make the regular document. As you make a rough draft, and we have guidelines for what should go in one of these things. It's called a pre, and you should do it. And so there's an institutional deadline. But LaACES management, as Colleen said, is not going to see the pre thing. It is really for your benefit, and it really does help for you to go through the process of creating the pre-PDR and the pre-CDR. You then show your preliminary design review in early February, and then it's due a week later at LaACES. The CDR is due beginning of April. You do your thermal vac test at the end of April. The flight readiness review, you should have that document done by 6th of May, but you notice that then we have a trip, May 15th to May 20th. That's when we travel to CSBF in Palestine, and you do your presentation the second day of the trip. So the Megasat itself gives you a set of simple measurements: pressure, temperature, humidity. That doesn't mean you can't do other things. These are things that have been done in the past. Intensity of radiation as a function of altitude, measurement of UV intensity, ultraviolet intensity, measurement of concentration of various gases. There have been some thermal measurements of the heat content of the Earth's atmosphere, measurements of airflow around at very high altitudes, measured the temperature outside, which turns out to be a real challenge because there are many things that can actually influence what you actually measure. Maybe you have something that you want to orient your payload. So you want to know which way is it pointing. So you could develop an inertial sensing system. These are all things that have been done among any number of other things. One of our goals is that there is a total eclipse. We had one just a few years ago. There's a second one. We will be leading a group of student teams during this total eclipse on the 8th of April. We will be going up to Illinois again. Our effort will include a practice flight during the October 14th annular solar eclipse. We will hold a competition for the LaACES 2022. So the people who work in that they will be selected for student payloads. So if you want to see what completed payloads look like, this is what they look like. These are actually from fairly early ones, because you notice the number at the end is the flight number. So that's the 16th flight is down at the bottom right. So science topics that we've done. So ACES 7 looked at solar cell efficiency. ACES 16 did cosmic ray intensity as a function of altitude. There's a temperature versus altitude versus time profile. We've done sound waves. So we've done speed of sound experiments. There are many things that you could think of doing. This is what the Columbia Scientific Ballooning Facility looks like. It's a bunch of buildings. And inside there is room to build very big payloads that are then flown under wet balloons that carry several million cubic feet of helium. They're huge. So our launch date is set for middle of May. And this is where you will actually do the final prep for your before your payloads are strung on the payload string, and then we take it out for launch. And the picture on the right shows the students actually doing their payload presentation there at CSBF. You have the CSBF staff and all the faculty there as well. What you do at CSBF after you travel there is you have basically a day to finally fix things. There are the inevitable small little glitches that crop up. There will be fixes like that. So we have a day to do that. And then by Monday evening, so we travel on Sunday, all day Monday, we make sure the payloads are going to work. And then Monday evening, we string up all the payloads. This is actually at the CSBF facility. And you see all the payloads. So you kind of see now what the typical payload looks like. There's a few radio beacons. There are payloads there from, let's see, we got a video camera. We've got McNeese State. They've got, those are the names of the various teams. Xavier had one. There is, of course, a parachute, because once the balloon gets to 100,000 feet, what we do is we cut it away. So it just goes up further and pops. If it pops, it tends to foul the lines. So we try to avoid that. And there's a parachute there at the very top, and that carries it back to Earth. And the total suspended weight, this is an FAA regulation. For ACES 60, it was 10.9 pounds. The FAA wants it under 12. Launch day starts very early, because you want to do this when there are not strong winds. And so you have to get up early in the morning before the heating of the ground causes the winds to grow. So we get up very early. You basically, what you do that day is turn on your payloads, seal up your boxes, and we walk it out to the flight line. And that second picture on the right is fairly close to launch. People are holding their payloads just before the balloon is released. And okay, let me see if this works. So we have a video camera, and we have sound. So we record during the flight. And so this is what it looks like from the point of view of the balloon. As you notice, the balloon twists and turns a bit, because those two lines hanging down make a kind of slow pendulum that rotates back and forth. Doesn't tend to swing so much, but it will rotate fairly easily. And that's what East Texas looks like.
So you can see just a couple seconds, like you can see the other balloon beneath it.
So this was actually a flight in which we did 2 balloon launches, and that large white spot on the other one was actually the other balloon payload. It may show up again. Yes, it's off to the, it's in the upper left corner there. There. Now you get up here, there's not as much air. You still have some of the rotation. You're well above the clouds now, and that is burst. That's 100,000 feet. And things are free falling now. Not enough air drag to open the parachute yet. And then this is much closer to the ground. There you go. That's what a flight looks like from the point of view. All right.
Great, thank you, Dana.
Is this the same thing, Colleen?
Yeah, it's just replaying.
It's just replaying. Okay. I believe all those dots out there on that one are those the oil fields?
I don't know. Probably.
Oh, this is the other, this is the 59 flight. Whoop, what happened? Stopped. There you go. That's from another view looking up at the balloon. So you're getting a really quick view. That large area right there that just passed is where they launch a 1,000,000 cubic foot balloon. So that's something closer to the size of the balloon that would fill a football stadium when fully inflated. And this is what it looks like very high up. You will notice the black of no atmosphere up there, so no more blue sky. You're well above the cloud layer, and of course that's the sun. And I think you can see that the Earth is curved. It's not that dramatic, but it's there. So you know any flat earthers, you can show them this. And that's cut away. And now everything's flying around and there's very little air. So you'll see all kinds of stuff fly around past you. And then the parachute finally kicks in and you descend. That's another view of the cut down. It gets pretty wild and crazy up there.
Yeah, so these are edited videos. Like there's, hours of footage.
Yes.
And
We have lots of video.
Cut them down. Yeah, so he'll cut them down, and it's very dizzying to watch. So imagine watching all of the live video and doing the editing.
The flight takes about 90 minutes to go up and a little over an hour to come down. And this one, let's see, is that one so it comes back down, but this does not come down in necessarily the.
You've got some good pictures in some future slides.
This is the same thing, isn't it? Yeah. Yes. Okay. So we track the payload because the vehicle, so we set up radio beacons, so transmitters that transmit a packet of data that contains latitude, longitude, and altitude, and maybe some information about your payload. That data is transmitted to a receiver, and the frequencies we use are frequencies that are allocated to amateur radio in the United States. All of the LaACES staff hold amateur radio licenses. If you want to do that, if you want to get an amateur radio license, you can. The other thing we use is, as we're driving around, we need to communicate between the vehicles that are chasing the payloads. So we will be using amateur radio frequencies to talk to each other, because that's much better than a CB radio. And we're in an area where cell phone service is very thin to none and not reliable. So the VHF, that's very high frequency transceiver, it works on 146 megahertz. The data is transmitted as a data packet, much like you get Ethernet packets over the Ethernet. It's very similar to that. It uses what is called the Automatic Position Reporting System, or APRS, which is a standard format to transmit where I am and what I'm doing. So the beacon reports the position. We have laptops, so this data, if you listen to it, is just a burst of sound. We have laptops with sound cards in them. The sound cards decode the sound, which is the data packet, and record it, and then it's displayed. It is displayed on a map. So we have software that then translates the position and puts it on a map, and that's how we follow it. It's basically waypoints that you are sticking on top of a regular GPS display. We typically are this way. We can actually stay to where we can see the balloon the entire time. It may be at 100,000 feet. A pair of binoculars helps, but we have watched balloons burst if there's no cloud cover. And we actually, while we could just let the balloon rise until it bursts, they're actually designed so that at 110,000 feet or so, they burst on their own. But it's usually better if we cut them away. We actually send a radio signal from the vehicles to actually cut it down, although our most current version can actually figure out when it's gotten to a certain altitude that it needs to initiate a cut sequence. So I said a flight takes about an hour and a half to go up and about an hour to come down. This is the flight profile. This is the altitude in thousands of feet versus time. The time is in Greenwich Mean Time, UTC, because that's the way the timestamps come from the GPS. And you see a fairly steady rise. And one of the things you will have to learn is this rate is 1,000 feet per minute. And this is one of the things you will hear throughout these lectures. This is something, I just told you something, you need to remember that something because it's part of your design. If you are going 1,000 feet a minute and you have, for instance, a GPS that is only good to 100 feet, if you're only going 1,000 feet in a minute, you don't have to record your altitude 100 times a second. There's no point in it. So that's one reason why knowing that rate is important. There is actually it's not exactly a straight line. There's a little wiggle, and what's happening is you are going up to about 40,000 feet or so. The temperature is steadily declining, and you get to a place called the tropopause where the temperature starts rising again. And we often see that affects the flight of the balloon because it's now going through an area. The air is getting thinner and thinner, but it's getting warmer and warmer. And these were two flights done at the same time, and one launched a little bit later. You'll notice that they didn't quite rise and fall. And you get to 100,000 feet, and then you notice a very steep drop. That is the free fall. and then somewhere between 40 and 60,000 feet, that it's no longer free fall. You're on a parachute, and the last part is carried back to Earth on the parachute. We've actually done an experiment, for instance, when it fell, we listened to the radio transmissions, which were Doppler shifted by the speed of fall, and we have seen fall rates of 10,000 feet a minute. So it's really going before the parachute opens. This is a picture of what the flight path asked. There was a question asked about how far they go. This is about 20 miles, if I recall. We launched from here, and we ended up over here. You will notice that there's an awful lot of trees and things here. We try to arrange the flight so that we don't end up a place where it's difficult to recover the payload, but there are no guarantees because this is uncontrolled flight. It's wherever the winds take us. Recovery. This is often the most interesting part of the whole flight. So 45 minutes to an hour, the payload is back on the ground. Where is it? Well, we roughly know where it is because we've been getting these radio data packets, APRS packets, so we know roughly where it is. And now we're somewhere in East Texas, and we have to recover. And they go from the very easy to the extremely difficult. So the first picture up there is very easy. Well, not as easy as you might think. This is East Texas. This is an open carry state. That you can't go on somebody's private property without their permission, and you see some barbed wire there. So it's not like you can just walk over there and pick it up because it's East Texas. On the other hand, if you end up in the trees, you can end up high up in the trees, you can end up lower in the trees, and then you have to get it out of the trees. So you are complicated with the fact that it's probably on private property, but now it's 75 feet in the air. So sometimes recovery is easy. It's on the ground. The hardest part is figuring out who the owner is and getting permission to go onto the property to pick it up. Frankly, most of the people in East Texas, once you tell them what you're up to, they're so curious, they often come along with us. Which is good because they often know the easiest way to get it and what to and a path that might avoid, like the really muddy parts. So it ends on a bush or it ends on the ground. Sometimes not so easy. So one flight involved flying shortly after this section of Texas had about the worst flooding it had had in several decades. As we were driving there, we would drive over rivers and watch the river be not 30 feet below the bridge, but like 2 feet below the bridge. So, and this particular payload ended up in a bottoms land. The creek that ran through it was known as Mud Creek. Most of this area had been washed out during the flood, which had finally receded. We did wait that long before flying. So we found a boat that was still there that had not washed away in the flood, but there were no paddles. So we were up Mud Creek without paddles. I know because I participated in that. I'm sitting right in the middle of that boat. This thing was 75 feet up. It required paddling 1.5 miles down this creek, which mostly had branches falling over it. And every time you went under one of these things in the boat, you ended up having a shower of spiders falling into the boat. That is a picture of me in the middle there in my hat This is after we cut the tree down, which took permission. It took a great deal of while, and to compound things, the person who cut it down actually cut it down the wrong way. So it fell into the creek. And shortly after this picture, I joined the tree in the creek. And in the end, we finally got it back, though. We have only lost about 1.5 to 2 payloads. One came back and half the payloads were gone. We never knew where it went. But we usually get them back. And this is how we went back and forth. Person with the hat in the middle is me, and I am using a waterlogged 2x10 as a kayak paddle. You want to know how much a waterlogged kayak paddle waterlogged 2x10 weighs? It's a lot. And the fun part was that this was great in open water. I could really get it going. And as soon as we got to where the branches were, my paddle would catch on the branches and stop our progress. So we have war stories. The point, though, is that it's always fun. You have war stories and you end up learning something, and you have acquired a set of skills that will serve you well after you leave your university. All right, that's all I have. Are there questions?